all, we are Pravallika
and Mateen. So, as a part of our ES116 Principles and Applications of Electrical Engineering course at IIT Gandhinagar, we will be analyzing the frequency response of two different sensors, a piezoelectric sensor and a photodiode.
We'll be plotting the magnitude response and phase response for both the sensors, determining some key parameters like the quality factor for the piezoelectric sensor and a 3 dB cutoff frequency for the photodiode. So, let's get started.
Firstly, we have the piezoelectric sensor. A piezoelectric sensor generates an electric signal in response to mechanical vibrations. We connect the sensor to an oscilloscope and apply a sinusoidal input signal with varying frequencies. So, the procedure goes like this.
So we have taken a 10 volt peak to peak sine wave as our input and we have connected it to the breadboard. And we have connected one wire of the speaker to the positive terminal, that is the signal, and then another wire to the ground. And then we have connected one wire of the piezoelectric material to the ground and one to the output. And to see the input signal in the oscilloscope, we have connected that through a wire. So in the channel 1 we can see the input signal which is in the yellow color, and through the channel 2 we can see the output signal which is from the piezoelectric material.
Experiment, we have plotted the magnitude response and the phase response of the piezoelectric sensor. This is the magnitude response graph. The frequencies at which the peaks occur in the magnitude response are the resonant frequencies of the piezoelectric sensor. At these frequencies, the sensor is more sensitive to vibrations. We want to find what the quality factor of each of these resonant frequencies is. So what is the quality factor? The quality factor is a measure of how sharp the resonance is. A higher quality factor means a sharper and a narrower peak. It is a ratio of resonant frequency over bandwidth. Bandwidth is the difference between the two frequencies on either side of the resonant peak, where the magnitude is 3 dB lower than the peak value. From this graph, we obtain that the resonant frequencies are 1200 and 3300 Hz. Their bandwidths are 450 Hz and 620 Hz. Therefore, the quality factors for both frequencies are 2.67 and 5.32 respectively. This is the phase response graph. The phase response shows a phase shift near resonance, confirming that the sensor reacts differently at different frequencies. The phase response exhibits a significant change near the resonant frequency. At frequencies far from resonance, the phase is relatively stable.
Now, let's go through the second experiment, which is with the photodiode. A photodiode generates a current proportional to the incident light. It is operated in reverse bias to increase the sensitivity and speed. A load resistor is used to convert the current into a measurable voltage. We apply a sinusoidal signal to the LED which modulates the light intensity. The output across the load resistor is observed on the oscilloscope as a function of frequency. Now let's go through the procedure.
So this is the input. We'll take 5 volt peak to peak and 5 volt DC sine wave, and we'll connect the input to the breadboard, the positive terminal and the negative terminal, and then the positive terminal of the input is connected to the LED and the negative terminal of the LED is connected to the 330 ohms resistor. And then there is another circuit, like we will give 5 volt power supply and that will be connected to the breadboard, and then the 5 volt positive terminal is connected to the negative terminal of the photodiode because it's in the reverse bias, and then the positive terminal of the photodiode is connected in series with the 10 kilo ohm resistor, and then the 10 kilo ohm resistor is grounded. We will measure the voltage across the 10 kilo ohm resistor through the oscilloscope. So the channel 1 is input and the channel 2 is output.
From the second experiment, we have plotted the magnitude response and the phase response of the photodiode. This is the magnitude response graph. It exhibits a typical low-pass filter behavior, where the response decreases as frequency increases. The 3 decibel point is the frequency at which the magnitude response drops by 3 decimals, which is approximately 30% from its maximum value at low frequencies. It indicates the frequency at which the photodiode's output starts to significantly weaken. A higher cutoff frequency means the photodiode is faster. This is a measure of the bandwidth of the photodiode. In the graph, we can observe that the magnitude response falls off at higher frequencies. It is due to the fact that the photodiode's internal capacitance and other factors limit its ability to respond to rapidly changing light signals. From the graph, we obtained that the 3 decibel frequency is 60 kHz. This is the phase response graph. It shows a gradual phase shift, confirming the system's frequency dependent behavior.
In summary, we analyzed the piezoelectric sensor, identifying its resonant frequency and quality factor, and studied the photodiode, identifying its 3 dB cutoff frequency. These experiments helped us understand the frequency-dependent behavior of the sensors, which is crucial for designing efficient electronic and optical systems. So that's it from our side. Thank you for watching.